morning, everybody. Let's revisit and revise the anatomy of Kernoff map that we have covered so far. So, a scientist by the name of Maurice Kernoff came up with an intuitive and graphical representation of any given truth table of a Boolean function. So, let's assume that we have this truth table. So, according to Uncle Kernoff, he said that this function has three variables. As such, I can represent it in a 3D space. So let's take a look on that. So as you can see here, this function is represented by a cube, whereas each point of that cube represents a row in the truth table. So the black row here represent that function was equal to 1 at that point. So that min term was used in order to formulate that function. So as you can see, guys, we have a black dot at 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and finally at 1, 1, 1. So as we can see, guys, we can group these 4 points to formulate another shape, which is a rectangle here. And that rectangle will represent what? A prime. Thank you so much. Whereas these 2 points can be grouped, guys, in a line, and that line can be further labeled by BC. What's not changing here, guys, is just BC, BC, okay? So at your level, guys, the Kernoff map can be simply represented by squares of maps that are labeled so that horizontally or vertically adjacent squares differs only in one variable. So here we have 3 variables, so we're gonna have a rectangle here, okay guys, and that rectangle can be labeled by rows and columns. So I choose the most significant bit here, A, to represent the row, whereas the B and C were used to label the columns, okay? So look at this. This row will differ from this row with just one variable, which is A. So A was A prime, and now it's become A. While here, each adjacent cell will differ only with one variable. So here, the only difference is just B, because now it's B in the negative, B is C, sorry, C, because C is now at the true state, and these two adjacent, the only difference is B prime, because B was equal to B prime here, and now it's becoming at the true state, and so on. Okay, so this format is recommended if the function are represented by the sum of minterms logical expression. So this function here, guys, if we look at this function f, and actually we can see that those 4, as a matter of fact here, we can see that these 4 can be represented by A prime by just looking at the truth table, because look at this. It's 1, 1, 1. Whenever what is not changing, B and C are changing, so it's just A that's not changing. Or we can go here at the truth table and place 1 at 1, 1, and then 1, and then 1. And then our goal is, and here we have 1 as well, yeah. And our goal, we will look at this Kernoff map and we try to group all the ones in the highest possible group that we can. So since here we have like 8 cells, I try to group them in 8. Unfortunately, I cannot, because I have 0 here and I have 0 here. Then I'm gonna look for a group of 4. Unfortunately, these can be grouped in a group of 4. So what is not changing? Just A prime. That's it. Now for this one and this, this one is not covered, so I have to cover it. Can I group it in a group of 8? No. A group of 4? No, I cannot. Group of 2? Yes, the only way I can do it is this way. And since A is changing from 0 to 1, I will just take the column label, which is BC. Okay, so this function f can be written in a simplified way by A prime plus BC. Okay? And as a matter of fact, guys, this, like this rectangular here, Kernoff map is actually what? A cylinder. And that's why I was capable to group like 1 and 3 here. Look at this. And all of them I can be like, oh, 0, 1, 3, and 2 can be grouped. Okay? Can be looped. Okay, guys? Now, let's agree on some of the terminologies that we introduced on the previous lectures, and we're gonna use it intensively here in this lectures. So let's recall, what is an implicant? So an implicant, guys, is simply a single one or a group of one in the kernel map of a given function. Okay, guys? So let's assume we have this function 2, 3, 5, 7, and this is at the canonical sum of a product. So that circle could be, this circle here could be 2, or could be 3, or could be 5, or could be 7, or a group of them, as we're gonna see later on. Okay, where here that one can be represented by what? By 0, because 0 doesn't belong to the function f at this Venn diagram. Okay, guys? Now, the product term or an implicant is called a prime implicant of function f if it is cannot be combined with another term to eliminate a variable. Okay? And the product term is called an essential prime implicant of function f if there is a min term that's only covered by that prime implicant. So in our example here, the prime implicant is the largest possible cube to formulate function f at a high state. Okay, guys? So in other words, we go to our kernel map here. And as a matter of fact, this kernel map has 4 ones because I have 4 minterms, 2, 3, 5, and 7. This is 2, this is 3, this is 5, and this is 7. And look at this. That 2 can be rewritten here by A prime, B, C prime. And this 3 can be written as A prime, B, C. And this, this one is equal to A, B prime, C. And this one is equal to A, B, C, because that is 7. So 7 is all of the variables at the true states, and it's producted, okay? Sum of the products, okay? A, B, C, okay? Now, let me ask you a question. Can I group this implicant or this min term with anything to eliminate any of my variables? The answer is yes. So like this one at cell label 2 can be grouped with this one. So I can eliminate what? I can eliminate C prime. Okay? Therefore, neither this one or this one is a prime implicant. Okay? Now, these two this one can be grouped with this one in order to formulate AC. Okay? As such, this term, min term, and this min term are not prime implicant. Now, can I group these two in a group of 4 to eliminate any of the variable here, AC? The answer is no. Therefore, AC is a prime implicant, as well as A prime B is a prime implicant. Okay? Okay, when it comes to the essential prime implicant, how we can capture and discover the essential prime implicant? We go to our kernel map again, and we will look at the one, and this one, if it cannot be grouped in any group of 2 to the power n, okay, according where n is the number of variables, that implicant that will be formulated from this one will call its essential prime implicant. Let's apply that on this example. So this one, my goal is to group this one in a group of 8. I could not. In a group of 4, I could not. In a group of 2, yes. And it will only be covered or looped in a group of 2 just this way. Okay? So therefore, I will mark this with a star, and I will say that the prime implicant resultant from this grouping will be called its essential prime implicant. And this one and this one can be grouped this way, and this one can be grouped this way, so I will not mark it, okay? However, this is a poor one and can be only grouped in a group of 2 by just this looping, okay? That's why I put the star here, okay, guys? Now, those two, I can group them again, okay? But remember, guys, the minimal sum of product of function f must include all its essential prime implicant of f. So since we covered all the one, this is a redundant one, okay? So this one, if I'm gonna get it, that will give me what here? That will give me AC, and this one will give me A prime, B, and all the ones are covered, so I don't need this one. However, I can write it and I will call it as a redundant implicant, okay? And it's not even a prime, like that one is a redundant implicant and is not a prime implicant, okay? If you did not catch it, I'm gonna re-explain it here again with more graphical interaction. So here, guys, after looping all the ones, you can see that this one, AC, is an essential prime implicant because this one can only be grouped in a group of 2 this way, okay? And it's still a prime implicant, okay? And this one, guys, here, can be only grouped this way. As such, A prime B is an essential prime implicant as well as a prime implicant, okay? When it comes to BC here, BC is a redundant implicant. Why? Because all the ones are covered, so I don't need it. So the simplified version of F, okay, version of the canonical sum of product of 2, 3, 5, 7 is simply AC plus A prime B. Okay, guys, let's take a look on a more complicated example. So let's suppose that I gave you this function f, and this function has 4 variables, and this function is written as the canonical sum of products where 0, 2, 5, 6, 7, 8, 10, 13, 14, and 15 are the minterm of this function. So if you want to write this function in terms of the variables in the sum of products, what you have to do, guys, so 0 will be written as what, guys, here? As simple as that. 0, it's A prime, B prime, C prime, and D prime, plus that's a producted term added with to formulate the sum of products, A prime, B prime, C now, and D prime, and so on. Okay, guys? So that is here is the unsimplified sum of products of function f. So if I would like to simplify this function, I can write the truth table here, and the truth table, so the function f is high whenever I am at minterm 0, okay, so that's I will place 1, and at minterm 2, at minterm 5, minterm 6, and minterm 7, 8, 10, 13, 14, and 15. So I can map this truth table into what? this truth table, I can map it into the my K map here. So K map, okay? So what I can do is, you know, like please pay attention that I used AB to indicate the row and CD here to indicate the column. So 0, 0, 0, 0, that will give me the cell for min-term 0. At min-term 0, I'm gonna place 1. Okay, here, so I'm gonna place 1. Then I have 1 where? At min-term 2. So at min-term 2, I'm gonna place 1. Okay? Then at min-term 5, I have 1 again. So I'm gonna place 1 here. Whereas the rest, I'm gonna put zeros, okay? So no problem. So if I continue doing so, what I'm gonna have is I'm gonna have this K map, okay? Now, what I have to do is apply the rules that I shared with you guys in order to find the simplified version of F. So look at this one here, guys. This one, first, my goal is to group all the ones in the largest group, in the largest possible group, which is in my example here, 2 to the power 4, which is 16. So can I group this one in a group of 16? No, I cannot. Can I group it in a group of 4, on a group of 8? No. In a group of 4, yes, and it can be just one way. Okay, that's why I put star here. Okay, now I move to this one. This one can be grouped in a group of 4 by taking the corners similar to the previous ones, or by going vertically. Therefore, I will not put a star. This is not a prime, it's essentially a prime implicant. Okay. Now, when it comes to this one, again, this one is not an essential one. This one is not an essential. This one and all of these, like they're not essential. Okay. Now, when it comes to this one can only be grouped in a group of 4 just this way. Okay, therefore this one and this one are essential. When it comes to these two, no, these two can be grouped this way or can be grouped this way, okay? And this one is a poor one as well and can be grouped just in one way, which is by taking the corners. So by doing so, guys, what I can do is look at this. So these 4s, in order to get the implicant from these 4s at the corners, this is the corners, okay? This is the corners. So what is not changing vertically, guys? What's not changing vertically from 0, 0 to 1 and 0? It's the B prime producted with what's not changing horizontally, guys. Horizontally, what's not changing? I have 0, 0 here and 1, 0. So it's D prime, okay? Now, for this column here, what's not changing to get that implicant is just simply it's CD prime, okay? And for this one, okay, for this one, so first I have to cover the essential ones. So for this one, it's gonna be like, you know, vertically that is not changing is this one, so that is D, and horizontally not changing, okay, by looking this, that is B. Sorry guys, here that's B, and this is D. Okay, so D. So I know for sure that B prime, D prime, and BD are essential prime implicants because they are formulated from the ones that have stars. Okay, this one is a secondary prime implicant because these 4 have already been covered. Okay, this one and this one have already been covered, and this one like covered these 2. So these only 2 should be covered either this way or this way. That's why it's called secondary. Okay, guys. So what are my prime implicant? Again, my essential prime implicant are B prime, D prime, and BD because they are formulated from one that has a star. Okay. Now, when it comes to like this one, CD prime, it's a prime implicant here because it has like these two that only be covered either this way or this way in 4, but they're not essential, okay? So those are non-essential prime implicant, okay, guys? So in order to find the simplified version of F for sure has to include, okay, let me erase this. F for sure has to include the two implicants that are essentially prime implicant plus either I'm gonna take this one to cover these two, okay, or I'm gonna which is CD prime, or I'm gonna take BC, that is BC, okay, guys, that is BC. I hope that's it's clear for you guys. Okay, let's move on to another topic here. Now, suppose you have two black boxes here, guys, and these black boxes, you don't know exactly how they're working, but the thing that I'm trying to say here is that digital circuit N1 will never produce a combination of 001 or 110. So in other words, the inputs for N2 will never include the combination of 001 and 110. So the questions that we need to ask is what value should F produce for the combination of 1 and 6? What are the values? So frankly, we do not care, okay? Actually, we're gonna use that combination to our favor. So let's see if we are gonna assume that function f will be equal 0 whenever I have 001, input 001, okay, and input 110. So if I have them equal to 0, now in order to write the function f in terms of the sum of products, I have just here and here and here and here, okay? So this one will be a prime, b prime, c prime, and this one will be a prime, b, c prime, and this one that indicate 3, so a prime, b, c, and a, b, c. So if I would like to simplify it just using Boolean algebra, guys, what I'm gonna take AC prime as a common factor, and this will be 1. And here I'm gonna take BC as a common factor, and this will be 1. So at the end, this function can be rewritten in its simplified version as A prime C prime plus BC. Now okay guys, let's see the behavior of the function f if we consider that both inputs 001 and 110 will give me 1. So this function can be rewritten by taking, that is what guys here, that is minterm 0, this is minterm 1, this is minterm 1, and this is midterm 2, 3, as well as 6 and 7. So if we rewrite them, that is A prime, B prime, C prime, and that is A, B, C. Now, how I'm going to simplify it? So I can simplify it by taking here, what's the common factor? A, B prime, A prime, B prime, this is a common factor here. As well as here, it's A prime, B as a common factor for these two, okay? And AB is the common factor for these. So after rewriting them, that will give me 1, that will give me 1, and that will give me 1. So the function can be rewritten as what? A prime B prime plus A prime B plus AB. Now, can I take it further? Yes, I can take it further. However, I have to utilize the fact that this minterm has at least like one variable shared with the other two minterms. Therefore, I'm going to copy that A prime B twice, okay? Okay, so by copying it twice, what will happen is I can take A prime here as a common factor, and I can take B here as a common factor. So my function is equal to, will be equal to A prime plus B. Now, if I compare this solution to the solution that I got when ABC was equal to 0 whenever I have like 0, 0, 1 and 1, 1, 0, which is that solution, which one is cheaper to implement? Apparently, this one has the cost of what here, guys? That this is the cost of it is equal to 2, whereas the cost of this guy will be equal to like this is 2 plus 2 plus 2, which is equal to 6. So apparently, like considering the function f will produce 1 whenever I have 0, 0, 1 and 1, 1, 0, will be cheaper for me to implement than if I consider it what? If I consider it 0. Now we can use Kernov map to do so, and we will use the x to our favor all the time. So as you can see, guys, you know, like this, I can you know, I will group these 4 in a group of 4, and then I'm gonna group these in a group of 4. Now when I group this in a group of 4, that will give me what? This one will give me B, because B is at the true state here, plus, okay, and for this, what is not changing here? What's not changing is the, here, not changing, it's the A complement, so A prime, okay? But not every time, you know, like the don't care, I should include it in my grouping, okay? So I should include the don't care in a grouping as long as the groups will become bigger, or to make it possible to reduce the number of the groups, okay, guys? Now let's suppose like I have this example, this function f, and this function is written as the canonical sum of a product plus, please pay attention that this DC here indicate the don't care, okay, and can be notated by X. So whenever you are writing the truth table, so we know that we're gonna put like, you know, 1 at 0, 0, 0s, okay, and at 0, 0, 1 we'll put 1, and at 0 we will look here, it's not included with the don't care, as well as it's not included with the function at at 2, so that's why we're gonna put 0 here, and at 3 we're gonna put 1. Now at 5 we will not put 0, okay? At 5, look here, 5 is included, we will put the X, the don't care. Now what you have to do is you apply it everywhere and map it to the Kernov map here and use the X to your favor. So by examining this Kernov map, we know that, you know, this 1 can be only grouped in a group of 4 by this way. That's why I mark this one and this one as what? To form an essentially prime implicant. When it comes to this one, look guys, for this one can be grouped in a group of 2 this way and this way by taking just these 2 corners, or by going this. Therefore, that's not an essentially prime implicant, okay? And I cannot group it in a group of 4. Now, this one is essential because it can be grouped, yes, in a group of 2 this way, but at the 4 level, at the quad level, it can be grouped in a group of 4 just one way, okay, which is by taking these 2, okay? Therefore, if I'm gonna like, you know, like look at this one, if I wanna get what is the implicant for this one, that's the implicant for this one. What's not changing here when I go like vertically, not changing the A prime. So I'm gonna put A prime and I have to product it with what's not changing here horizontally. That's then the not changing here, it's the D. So that A prime D is, I know for sure it's an essential prime implicant, and for this gentleman it's gonna be A, and what's not changing when I go here? D prime. okay, AD prime, okay, for this one, that is plus AD prime. Now, for this gentleman here, for this group of two, that's not like an essentially prime implicant, and therefore, you know, but I need it. It's a prime implicant in my case because I need it to like to cover all the ones, okay? So to get that, that is this, because it's a group of two, it will give me like an implicant with three literals. So what they are, so if I'm gonna go here, what's not changing, it's gonna be B prime, like vertically, and I'm gonna take the code of the column, which is C prime and D prime. Okay, guys? So look at this. Let me rewrite it properly. So the essentially prime implicant, as I mentioned, are this quad as well as this quad. Now the prime implicants are all of them, okay? So the prime implicant is this, like this one, as well as this one, as well as like if I group these two, like by taking the corners here, or if I group them here. So I'm gonna have four prime implicants. Now, those are not essentially prime implicants. If it comes to, I will take just one of them to formulate the minimized version of my function f. I hope that's clear for you guys. Now, one last thing I need to cover with you is how to get the product of sum using a kernel map. So assuming that we have this function, and this function is written as the sum of products, so we will look what we are missing here. We are missing for sure the 4 because 0, 1, 2, 3, and now here I'm missing 4 and 6 because here there is a gap, and 9 and 11, 12, 13. So those will be, guys, what my product of sum max terms, okay? So when I fill the, I will use the same thing, the same terminologies to because I have 4 variables, it's gonna be like a 4x4 kernel map. However, guys, like, you know, after filling the ones for the sum of products, we will just group the zeros, okay? Now, this 0 can be grouped in a group of 2 just this way, okay? That's is essential. And this can be grouped in a group of 0 just this way, so that's why it's essential. Now, these two can be grouped either using the blue rectangle here, or I can group them this way, guys, here, with no problem, okay? Okay, so that is, you know, those are non-essential prime implicant, okay? EPI. So now to take the code, like for this one, for the red one, now we will, okay, we will examine this grouping vertically. So what's not changing here? What's not changing here? Here, what's not changing when we go here is just the D, and the D is at the 0. So remember, the product of sum, 0 will give me the high state. Okay, 0 will have the positive logic. So that's why I choose D, okay? And vertically, it's A prime, because, no, it's A and B prime, okay? But all of them, what? A plus B prime plus all of them are summed, then will be producted, okay? Now, when it comes to this gentleman here, okay, for this gentleman here, so if I go vertically, the thing that's not changing here by looking here, it's the D. Then I have here I have A prime, because A is, guys, what? At 1. So A prime for the product of sum plus B, okay? So that is for this one, okay? And now D prime here, okay? And for the blue one here, the blue one, like for sure A and B will be like A prime, B prime. And look here, what's not changing vertically is just the what? Just the 0 will indicate C. at the positive logic because we're taking the product of sum. Okay, guys, so let's summarize the main objective of this module. So basically, if I give you any function, that function you should write it, describe that function in terms of the input as well as in a truth table format. Okay, then you can simplify that function by mapping this truth table to a kernel of map. Okay, then after getting the kernel of map, you can get the code for each implicants and categorize these implicant to essentially prime, non-essentially prime, prime implicant, redundant implicants. And remember, the fmin will include just the essentially prime implicant plus any redundant that will cover all the ones, the remaining ones. And if you write your function f in terms of a sum of product, you can implement it with ANDing each term and then ORing the resultant. Or if you implement it with a product of sum, what you have to do is you're gonna OR each term and then product it with a big AND at the end. And if you would like to convert the sum of product notation to an AND only, you will use NAND only. You will use De Morgan. Like suppose that we have this F equal to AB plus CD. That is what sum of product prime that will be equal to A, B, C, D. Okay, so this is the whole thing prime. And if you would like to convert your product of sum to an OR only, it will be the same. So F equal to, let's say, A plus B, okay, ANDed with A uh, uh, and C, okay, A plus C. So prime, what will happen is take the first prime in, get it in, so you have to change it, so it's gonna be A plus B, that's a prime, that is plus, that is A plus C prime, and remember we have a bigger prime, so that's an OR only. Okay, guys, and by this slide we are gonna conclude the main objectives of this module. I'm gonna call you for a live session next week. Thank you so much.